It's quite often to encounter heat transfer problems in radial or cylindrical geometries, especially when we are dealing with heat exchanger or let's say transport of a hot fluid through a pipeline. So let's assume we have a hollow cylinder, which is a pipe. So just putting that on with the internal radius of Ri and external radius of Ro. And let's assume we know the temperature. This is Ti and To. And essentially, this is a pipe. Now, if you recall, Fourier's law of heat conduction for a radial geometry, QR is minus Ka dt dr. If I replace the area for any of the radius, it's going to be minus 2 pi rk dt dr. Now, for this specific case, we have two boundary conditions, T is equal to Ti at R equal to Ri, and T is To at R equal to Ro. And we know the heat flow rate for a cylindrical coordinate, QR, is going to be 2 pi KL Ti minus To divided by natural log of Ri divided by Ro. Now, from this one, we can do a little rearrangement and then get the thermal resistance of conduction here, which is going to be the temperature difference, delta T, divided by the heat flow rate. And if we do the math, it's going to be natural log of Ri over, sorry, here it's going to be Ro. O divided by Ri, Ro, Ri divided by 2 pi KL with the unit of Kelvin per watt. So this is going to be the conductive thermal resistance in a cylindrical geometry when we have this single layer that is resisting the heat flow for a multi-layer composite cylinder. Multi-layer composite cylinder, let's say as in insulated pipe. Then the pipe is not just only made of one single material, it could have different sort of material. Let's say internally we have a coating. Let's assume this is the coating and it's a thick coating or thin coating, doesn't matter. Then we have the actual pipe. So that could be another material. I'm just looking at the cross sections. And then we could have some composites here, some insulations here around that. So let's say this is R1, R2, R3, and let's say this is R4. And we know the temperature here at the internal of the surface. Let's say this is T1. And this is T4 in the outer side of this pipe. And assuming that each of them have a different conductivity, let's say this is Ka, Kb, and Kc. Now, similar to what we did for a multi-layer solid wall in a Cartesian coordinate, then we can get the overall or the heat flow rate that is pathing. So there is going to be a heat flow rate that is pathing through pipe, and that heat flow rate Q is going to be T1 minus T4, which is the temperature difference. and we have these layers in series. So this is gonna be natural log of R2 or R1. R2 and R1 is Ka plus natural log of R3, R2 with Kb, natural log of R4 by R3 by Kc, and everything is 1 over 2 pi L. So where the resistance, let's say the thermal conductance resistance for layer A or the first internal layer is natural log of R2 R1 divided by 2 pi L Ka, and so on. So we can write it for any other layers. This is only 3 layers, but it can go to more than 3 or any type of layers. Another situation that can happen is, let's say there is a convection inside the pipe and outside. Like let's say this pipe is carrying some hot fluid. So because the fluid is just moving, we would have a convective mode of heat transfer inside the pipe. And let's say outside there is a wind or air is just like passing through. So we would have outside convection too. So for that specific case or for that case, so let's say if there is convection inside and outside pipe, outside pipe, let's say with Hi and Ho as a heat transfer coefficient. So let's say we have this pipe and it's carrying some fluid, and then here we have Hi, here we have Ho outside that. So there are some flow and there are some flow getting inside that, and this is K. So it could be one layer or it could be multiple layer. Then what we would have here for Q is T of inside minus T of outside divided by 1 over 2 pi R1 L Hi plus sigma of Ri divided by Rj. I'm just writing for general multi-layers anyway. 2 pi kjl plus 1 over 2 pi Rn L Ho, which is in the outside of that. Now, what are I and j here? I changes from 2 to n, and j is I minus 1. Don't get confused that with the hi. So this is for the multiple one. Like you would see in the resistance one, we have 2 terms related to the convective heat transfer that happens here. Now we can have similar things for a spherical geometry. Spherical coordinate. An example of that would be like this special storage vessels for gases, let's say, for special storage vessels for gases that generally they are in a spherical geometry. Then we can reach to the heat flow rate, which is going to be 4 pi k 1 of Ti To 1 over Ri minus 1 over Ro. So the RT and conduction is going to be 1 4 pi k 1 over R1 minus 1 over R2. I would recommend you to go and derive it yourself.